Deep learning has been pretty successful in the past decade. Although we know it takes inspiration from the way the brain works, there are some reasons why backpropagation cannot be the algorithm the brain runs on. And there are mainly two constraints the computation of a neuron needs to fulfill in some way to be considered biologically possible. So the first is local computation. So a neuron can only perform computation on the input neurons, that is the activation from the previous layer, and the synaptic weights. So those will be the model weights. And second, the local plasticity constraint. That is, the neuron can only change its synaptic weights by looking at the activity of the post-synaptic and pre-synaptic neurons. So that is, the computation of the activation must be local, so that would be the feed-forward pass, as well as the update rule that must also be local. And the first condition is generally satisfied in deep learning architectures. The feed-forward pass is local. But the second is actually not. Backpropagation is not local. And assuming we are talking about neurons arranged in a hierarchical way, where the output of one neuron is the input of the next neuron or the next layer, it is not clear how the brain could implement something like the chain rule, where it iteratively compute the derivative of the synaptic weights at a given depth in this hierarchy. Okay. So in fact, it is difficult to conceive that the brain might be optimizing something like a global loss even. This is normally associated with a supervised learning paradigm, which is normally common in deep learning, which is quite unlikely to be the way the brain works. Instead, what is likely to be happening is that each neuron optimizes a local loss following a local rule that only involves information coming directly from its neighboring neurons. And in the past year, a paper has been published that shows how backpropagation can be approximated by such a set of local computation for the updates. And this work is very, very interesting, builds on the concept of free energy, the free energy principle, and predictive coding. So the free energy principle can be seen as generalization and an extension of predictive coding. And a tool like backprop in deep learning uses gradient descent, but now each neuron has its own local loss. So each neuron has its local loss and the local loss function, and that depends only on information that could be plausibly, biologically be available to a real neuron in our brain. And another advantage of this approach is that it is based on Bayesian statistics principles, and is therefore natively able to deal with noisy inputs, sensory inputs, and can also not only output the value of an activation of a certain neuron, but potentially its variance too. And that can be thought of as a measure of the confidence of the activation of a neuron. So the concepts and math behind the free energy principle are a bit different from the normal deep learning stuff. So I'll start with a basic example following this excellent and enlightening tutorial from Rao and Ballard, which I strongly suggest to anybody who wants to dive a little bit deeper into this tutorial and understand this concept a little bit better. The tutorial it starts by imagining an animal that's to infer the diameter of a food item based on the light intensity it observes. So the animal in this case has only one light intensity receptor neuron, and the signal or activation of this neuron is very noisy. And also the intensity of the light coming from this from the food item is the square of its diameter. So this we assume this for sake of simplicity, but it's also a reasonable assumption to make, because to make the light reflected by an object is proportional to its area. And since the signal that the animal receives, we call it U, is noisy, we assume it's to be normally distributed. And the mean of this distribution, we assume it to be the square diameter. So P of U given V expresses the conditional probability of perceiving light signal U if the diameter had value V. And since the signal is noisy, the best the animal could ever do is when it receives signal U is to find the value of V, for which the probability of P of U given V is maximized. So he wants to find out what is the real diameter of the food item. And also, one thing we might consider is that if the animal has some kind of statistics somewhere in its brain that expresses how food items with diameter V occur in general, not conditioned on any visual inputs he receives. So that could express, for instance, the fact that in an environment where this animal lives, some food items with a certain size are fairly common, so with middle size, and say food items with extremely high, or extremely large, or extremely small, they're less likely. And this is what a prior v does, and we also assume this to be Gaussian. Then using the Bayes theorem, the animal could be able to compute the posterior probability, P of v given u, which is the probability of the diameter of the food item being v, given that the animal receives signal u. And here, P of u is a normalization term and it is equal to this thing. And there's a number of problems with the animal computing this, the most likely foot diameter v in this way. First of all, because the function g relating the variable to infer and the sensory stimulus is nonlinear, so it's this quadratic function, there's no guarantee that P of v given u is a normal distribution. So P of v given u is this final result of the Bayes theorem. And in fact, the distribution might require us to calculate, this could be an arbitrary distribution. And to compute the optimal value of v, we might need to calculate every possible value of v of every possible probability P of v given u for each possible value of v, instead of having some summary statistic like the mean and the variance. And if you had to write a script, for instance, to find a value of the maximum likelihood in an unknown distribution, an arbitrary distribution, would probably involve checking a distribution for any possible value of v, and that is not very efficient for the brain to do, and it's probably not what it's doing. And secondly, the computation of the posterior distribution P of v given u involves computing these normalization terms, and we evaluating such an integral, if the distribution is continuous, could be challenging for a biological system and is therefore not considered plausible. So let's denote the most likely size of the diameter v by calling it phi. So phi is the most likely size of diameter v. It is reasonable to think that the brain does not keep a representation of the whole distribution, but only an estimate of how likely is the most likely value of phi. So that would be P of phi given u. So now we have to figure out a way, how does the brain find phi that maximizes the posterior distribution P of phi given u without having access to the whole distribution? So to find that out, we have to first rewrite the numerator of the quantity we want to maximize by taking its log. So that will be the numerator of the Bayes theorem equation. The log of the numerator can be decomposed as follows. So we define this as f, the free energy. We can do this according to this property of logarithms written here. We can optimize f instead of the original posterior probability because the optimal value of v is going to be the same whether or not we divide it by the prior P of u. Okay? And the next step is to substitute both P of v and P of u given v by the normal distribution. So we know both of these probabilities are parameterized by normal distributions. So the equation of the normal distribution is given by this, and it parameterizes both P of v and the prior and P of u given v. So by substituting in the free energy equation, that gives us the following. And then by taking the derivative of f with respect to phi, that gets us this thing right here. So right here, I went a little bit fast through all this derivation, but if you want to check it that all these derivations are correct, I suggest you pause the video and take a moment to check that everything makes sense for you. And once we get here, we can run our gradient descent algorithm and find the optimal phi. So this amounts basically to changing phi over time. So if we discretize time at each time step, proportionally to the derivative of f with respect to phi. And this can be written as phi dot equal df divided by the d phi, where phi dot means the rate of change of phi with time. And intuitively, if we look at the equation, we can see that there is kind of a force in the gradient trying to pull phi towards the prior VP, and that is the first term. While the second term is kind of trying to pull it towards the sensory stimulus u, and that is receiving, right? That is the real light intensity that is seeing. And it is important to notice that we did not need to evaluate the whole distribution P of phi given u. We just follow the gradient, and that gets us to the most likely value of phi. So we went through all this, and but we want to know how. So this could be a way in which you could infer this optimal value of phi. But we're able to efficiently infer this diameter of food item by performing gradient descent over phi variable over many updates. But we don't still, it's not clear how like a neural circuit could implement this kind of logic in the animal brain. So we'll now try to reformulate this logic in a way that can be plausibly be computed by a few neurons in an hypothetical brain. And we start by noticing that there are two terms in the gradient of f. This will be, they're kind of similar, these two terms. They kind of express a difference or error weighted by the variance of the corresponding distribution. And for the formulation of this neuron implementation, it is useful to create two new variables that each for this new term, two new terms. And these two new terms are the prediction error epsilon u, that expresses how much light intensity differs from the animal expectation if the size of the food item was phi, and epsilon p denotes how the inferred size different from the prior expectation. Then our previous gradient equation, if we substitute these two definitions, simplifies to this equation. And here we assume that the variables sigma p, sigma u, and vp correspond to the synaptic weights, and that is, they don't change from observation to observation, and they correspond roughly to the model parameters in deep learning setting. The stuff you normally learn using stochastic gradient descent. And while phi, epsilon p, and epsilon u, these are the sensory inputs that are maintained in the activation of the neurons. And this will be the equivalent to the layer activation in deep learning. Therefore, it can be a little bit confusing that we are not running gradient descent on the model parameters, but on the activations instead. Since in deep learning, these are just computed by doing the so-called feed-forward pass, right? So this is one of the differences between deep learning and predictive coding. Here, the activations are not computed in one iteration, but are computed over many iterations using gradient descent. We'll see later how the parameters of the network can be also optimized, but for now we pretend they're given, they're fixed also. And to continue our neural circuit implementation of the estimation of this food item, each neural activation should update itself in a way that the whole system kind of converges to the optimal value of phi. So let's pretend there's a neuron or node in a graph for each of the variables we are updating. So there will be phi, epsilon u, and epsilon phi. So we have seen how the phi neuron updates itself, namely by following this gradient right here. But we can see that the gradient of f depends on the nodes representing epsilon u and epsilon p. Now let's pretend, instead of trying to figure out what the updates rules for epsilon p and epsilon u are, let's pretend they're given to us, and they are these. And that gives us the activation, these two equations, they give us how the activation of the neuron epsilon p and epsilon u should change with time. And we can check the dynamics specified by these equations. They kind of converge or have these values right here as their fixed point. And this means that they converge to these values when we run gradient descent. And this is normally done by setting the derivative with respect to time, that would be epsilon p dot and epsilon u dot, to 0. And by then solving the equation that we get by doing so, by solving them for epsilon p and epsilon u, we recover the original definition equation of these two quantities, the epsilon p and epsilon u, which means these are the fixed point of the dynamics that would be the points the dynamics converge to. And when we set epsilon p and epsilon u to 0, that is intuitively to see when there is no change anymore, where like the gradient tells us there has to be no change anymore in how we update these two neurons. We want to see what are the values of those two neurons in the case that we don't update them anymore. All right. Note that also finding the fixed point by itself does not guarantee that there aren't going to be any oscillation in the learning dynamics, or that this fixed point is going to be a stable one. And actual Bogash in the paper goes a little bit further in describing how you could guarantee that this fixed point is a stable one, and so forth. So let's consider the computation unit nodes in this graph. The node epsilon p right here receives excitatory input from the node phi. Inhibitory input, that would be like a term with a minus sign. So excitatory is a term with a plus sign, and inhibitory is a term with a minus sign. An inhibitory input from the neuron via connection with strength Vp, and an inhibitory input from itself via connection with strength sigma p. So implements this equation here respectively. So far we only considered the dynamics of the activation of the neurons while keeping the synaptic weights unchanged, basically. And we said this is because, unlike backprop, where the feed-forward path results in the final estimation of the activation, in this predictive coding, instead, the activation have to converge to the final activation by using this local gradient descent, and that is without backpropagation. That's what local means. And so what is done in one iteration in deep learning is done here in multiple iteration until convergence. And that is kind of the cost of only having local update rules. We now will see how predictive coding can also update the synaptic weights, or what is the update rule there. When updating the synaptic weights, we want them to change in a way that makes the visual stimulus, so that would be in our case the light intensity is perceiving from the food item, most expected or less surprising for the neural circuit. And in other words, we want to choose the synaptic weights parameters that maximize P of view. So P of view, if you remember, is this like normalization term, this integral in the denominator of the base theorem. And it is itself dependent on our prior for the foot item diameter, P of V, and P of view given V. And these are distributions that are parameterized by the mu's and sigmas that we want to optimize. And since this quantity is not tractable, or at least we know of no organism that has been found to do so, we instead maximize for the joint probability of phi and u. And to understand why we can do this, we have to take a look at the free energy principle. So as we said before, the posterior probability P of V given u could have quite complicated shape, and for this reason could be quite hard to optimize. Instead, we could try to approximate it with an arbitrary distribution of known shape. So that would be kind of, if we want, a normal distribution, right? We could try to approximate it with a normal distribution. And for which we only need to specify a mean and a variance, for instance. But in the tutorial, the author Bogage even goes a step further and uses a delta distribution instead. This is a distribution that has all of its probability mass concentrated on one point. So its probability is 0 for all values except for phi, where it's 1. And the integral of such a distribution, the delta distribution, still sums up to 1. So these are facts that we need to know about the delta distribution. And since we want to approximate P of V given u with this delta distribution Q of V, it is natural to evaluate some measure of the similarity and try to maximize it. So we want to make them as similar as possible. As a common measure of this dissimilarity between distribution is the so-called Kyle divergence. And in this video, I won't spend much time talking about the Kyle divergence, but if you don't know how it works and what it is, you can. I advise you stop this video and check a video I put in the description. It does a great job of explaining it. And for us, for now, it is enough to know that the more different two distributions are, the higher the value of the Kyle divergence is going to be. And its minimum is 0 when two distributions are identical. The Kyle divergence between the posterior distribution and the delta distribution, Q of V, can be written like this then. So now we are looking for the center of the delta distribution phi, such that the Kyle divergence is minimized. However, directly doing this can still be intractable, as to evaluate the posterior P of V given u, we still have to use Bayes' rule. That involves the integral in the denominator and all that, and we want to avoid that. So we try something else instead, and we try to reshuffling the terms a little bit. So we know P of u given V can be rewritten as follows. And if we plug this in the Kyle divergence, we can rewrite it in this way. So in the second term here, we use the fact that the integral of Q of V is equal to 1, as we said before. And also, let's call the negative of the first term the free energy. So right here, the first term of the last equation we get, let's call it the free energy, or F. And this might seem a little bit arbitrary now, but we'll see how this quantity ends up being the same free energy that we used before when optimizing or finding the best phi, the phi that maximizes the likelihood. So then the Kyle divergence can be rewritten as this. And since we only have control over Q of V, and in the second term the logarithm of P of u does not depend on Q of V, or on V for that matter, we know that the value of phi that maximizes f is also going to maximize the Cal divergence. And assuming the Q of V is a delta distribution, we can further make some other simplification in the expression for f in this way. So here, in a transition from the first to the second line, we use the following property of logarithms. And in transition from the second line to the third, we use the property of the delta function with center phi, that for any function h of x, the integral of delta x times h of x is equal to h of phi. And that since phi is the only x for which the function delta is non-zero. Also, since the value of the second integral in the second line of the equation above does not depend on phi, we can treat it as a constant. So this constant C1, we can ignore it and rewrite the joint probability P of U and phi like this. So that would be the same quantity, the same thing that we saw before in the numerator of the Bayes theorem, and that would be, and its log is the same thing that we denominated before as f. So then if we take the logarithm, is exactly the same thing that we saw before, and we in the same way that we did before, we can use the property of logarithms and rewrite it like this. So the question we want to answer is why we could choose to maximize the free energy instead of maximizing P of U when trying to optimize the model parameters. Remember, we're still talking about the model parameters. We're taking this detour through the free energy principle because we want to justify the way that we optimize for the model parameters. This is because we can rearrange the Cal divergence equation from before like this. And since the Cal divergence is non-negative, f is a lower bound on the logarithm of P of U. And therefore, by maximizing the free energy f, we're also maximizing the log probability of the sensory input u, which is what we need to do in order to optimize the parameters. And if you're familiar with variational autoencoders, there's the same trick used there when the free energy is the same as the elbow or the evidence lower bound. So we did all this detour to basically to justify the way that we optimize for the weights. So coming back to the weights, that means that we can use the same quantity used before to optimize for the phi, the activation phi's. We can use the same quantity free energy f and differentiate it. This time, instead of respect to phi, with respect to the synaptic weights or these model parameters sigma u, sigma p, and vp. So starting from the expression for f that we know from before, we can get the derivatives with respect to the synaptic weights parameters like this. And we could check the learning dynamics resulting from this equation, and to check that these learning dynamics are correct, we should look at the values of vp, sigma p, and sigma u, and when the respective derivatives are equal to 0, we should check that they converge to their definition or to fixed points that correspond to their definition. And this is the same procedure we did before for phi, epsilon p and epsilon u, but I won't go through the same procedure now again. If you want to see how that goes, you can check the paper that I put in the description where I do all these computations. And if you want to rewrite the previous learning dynamics in a more inference dynamics in a more compact form, we can still use our previous definition of the error terms epsilon p and epsilon u, and substitute them in the previous equations for optimizing the parameters of the model, and we get this system of equations right here. And note that all the update rules now only use information that are local. And we can also check that the model is Hebbian because its updates only depend on the product of pre- and post-synaptic activation. So here the pre-synaptic activation can also be 1, or can be both the same quantities, since there are connections that lead back to the same node or neurons, like this sigma p or sigma u connections. And this means we satisfied all the constraints that would make this circuit something that can be actually implemented in, as a network of actual neurons in the brain. So the last thing that we need to talk about is the relationship. So is learning the relationship between variables. So here we have assumed that the animal has some innate knowledge about the fact that there is a quadratic relationship between the light reflected and the diameter of the food item. But this is not the case because, I mean, we want to create a kind of a general algorithm here. We want to formulate a general learning algorithm here. So we have to make an assumption that no relationship between variables such as these is actually there in this network of neurons. So instead of assuming that the function g, this function relating these two variables, is this quadratic function, we instead parameterize this function with theta. Okay, and then we change theta as our parameter, and we try to learn theta. So we can rewrite our inference equations now using this new parameterized function g, and that would give us this equation right here. But we could even go one step further and include the activation function like this. So an activation function like h, that could be a nonlinear function like a sigmoid function, and we first pass the inputs to this function and then multiply by theta. And by substituting this new parameterization of function g in the equations, we get the following. So next, we want to learn theta too, right? We want to learn since this is a general learning algorithm, we want to learn the parameters theta that correspond to the way that the relationship between different variables parameterizes the relationship between different variables. So here we still write down the free energy, but we substitute for g, we substitute this new parameterized function that is our g now. And by application of the chain rule, we can get the gradient of f with respect to theta that turns out to be this one. So we have now seen how learning can be implemented in the logic of such a simple neural circuit. And the only thing that is left to extend this to multiple variables. So basically, if each neurons can have multiple inputs and there are more of such neurons, we want to see how that works. And this is done by introducing vectorized inputs and outputs. Basically, inputs and outputs are now vectors and not just scalars as we pretended them to be up until now. And this extension is pretty straightforward. I won't get into the weeds on how to do that. But again, you can read the Bogash paper for all the details about that. For now, I will skip this step. And we can start feeding the output of each such layer of neurons to the next layer. And so we can create a hierarchical structure that now really resembles a neural network or a deep learning architecture. But here it conforms to all these biological constraints that we started to list at the beginning. So local computation and local plasticity. It is important to notice that we are dealing here with vector quantities instead of scalars, as we just said, as in the previous equations. But these new equations that we see, that correspond to the hierarchical model, they're still pretty similar to the previous equation, the simple one for the one neuron, one input case. Here, the parameters theta I and sigma I determine how the mean and variance of the activation at one layer depend on the activation at the previous layer. So, as we said, these are not too different from the equation that we've seen before. And for instance, in this equation that we've seen before, the second term here would correspond to the last layer of the hierarchy, as its prior does not depend from the activation of even higher levels, since there are no higher levels. And this can be seen in this diagram. And the first and last equation, however, those can be generalized to arbitrary many numbers of layers. So these two equations, here the first and the third, they can be generalized as for any number of layers. And here, to understand how the subscript u and p in the normal case and the previous case change to this I subscript for the level in the hierarchy, we can pretend to understand how that works. We can pretend that the activation from the level below are treated here in the same way the sensory stimulus u and was treated before. And that the prior, instead of being fixed, depends from the activation of the layer above in the hierarchy. So we treat the layer below as the sensory stimulus and the layer above as the prior, except for the last layer, as we've seen. And this whole thing can be seen as the original predictive coding framework introduced by Rao and Ballard. That can be introduced like this. Can be summarized like this. Sorry. So the inference step, unlike in deep learning, takes multiple iterations, as we said, And each iteration, every activations, so this would be the phi's, changes to minimize its prediction error of the activation of the lower layer neurons. So this will be the lower phi's. This all while the weights remain fixed. So in other words, the layer above tries to guess the value of the activation of the layer below, and this guess is compared to the actual activation to compute the error. So this error is passed back up to the layer above, so that the activation is changed to minimize the prediction error a bit more. So this happens simultaneously for all the neurons at all levels in the hierarchy. And this implementation, this is implemented by having some of the neurons that are dedicated to representing this error. So this will be these epsilon neurons. And these error neurons can be actually found also in mammalian brains, or like there can be found neurons that can plausibly be doing this, be having the same role that these error neurons have in this kind of computational models. And that was proposed by, I believe, by Rao and Ballard back in the 90s. And however, this thing of kind of guessing the level below of the activation level above, guessing the activation level below, is not the only thing that the neuron is trying to do. It is also simultaneously trying to not to change too much too fast, or else the neurons above him will have a harder time in catching up in predicting its value as it's moving, because also the level above this neuron is also trying to predict the level of the value of this neuron. So if you're phi, the game you're playing is this one. You try to change your value so that while keeping the weight sigma and theta constant, your prediction of phi I minus 1 is more accurate, but at the same time you don't change too much from the prediction of phi I plus 1. So this is the inference dynamics. The synaptic weights learning dynamics then changes the weights as well accordingly. And it is important for these two dynamics to have very different timescales. That is, for one to learn much slower than the other. And if you think about the animal example, the inference dynamics that allows it to get the correct diameter of a specific item of food should be much faster than the learning dynamics that allows it to become better at estimating the diameters of food items in general over the course of its life. And in the paper, Predictive Coding approximates backprop along arbitrary computation graphs. The author first let inference dynamics run until it converges, and only then they make one iteration of weights update. And it should also be noted that this is not a supervised learning algorithm, right? There's no targets answer that the neuron is trying to fit in this case. So there's no target answer that is trying to fit. What a network is doing instead is creating a model of different variables in the world related to each other in an unsupervised way. And in the same paper, the author also gives a general recipe on how to modify this unsupervised learning predictive coding architecture that I described here to perform supervised learning like a normal deep learning architecture. So I think this was enough for this video. This should give you like a complete, simple, but self-contained description how predictive coding and the free energy principle work. Until next time, bye.